Hey everyone, so today we're gonna learn how to solve ODEs using the undetermined coefficients method. Without further ado, let's go to our first example. Hey everyone, so this is our first example of solving ODEs using the undetermined coefficients. So we're gonna apply the superposition principle, which is just y equals yc plus yp. We need to solve for both the homogeneous part and the non-homogeneous part, which is the yp. So solving the homogeneous part, which is the yc, is pretty straightforward. As we can see, r squared plus r minus 6 equals to 0, and we can factor this out, becomes r plus 3, r minus 2, and so equals to 0, and then we'll get our yc is equals to c1e to the negative 3x, because r plus 3 is r equals to negative 3, plus c2e to the 2x, likewise. And we're going to denote this equation with the first equation. And so let's solve for our second equation, which is the non-homogeneous part. As we can see here, our right-hand side, we don't have it as equals to 0 as usual for like solving homogeneous ODEs. We have 18x plus 1, and so it is in fact in a polynomial form, and we will need another polynomial form to solve this non-homogeneous part. So let's call our yp here into ax plus b. In fact, this is a polynomial form, taking the first derivative, which is a, taking the second derivative, which is 0, because a is just a constant. And now let's apply our equations here to our original ODE and plot for y double prime and y prime and also y. And so we can solve for our both of our coefficients, which are a and b. So plugging them in, y double prime is equal to 0, and we can ignore that. Y prime is a, we can plug that in, minus 6 times ax plus b, so negative 6 times ax is negative 6ax, minus 6b equals to 18x plus 1. And solving for this, we can see that our a minus 6b doesn't have any x here, so we can equate them to 1, and our negative 6ax is equals to 18x. And solving for the second equation here, we get a equals to negative 3. Plugging a back to our previous equation, we'll get b equals to 1 plus 3 is 4, 4 divided by negative 6 is just negative 2 over 3. And so plugging back our a and b to our yp here, we will get yp equals to negative 3x minus 2 over 3, and this is our second equation. And so we just plug both equation, our first and our second equation, to our superposition principle that we write down at the start of the problem, and we'll get our final solution as y equals to yc, which is c1 e to the negative 3x plus c2 e to the 2x minus 3x minus 2 over 3. And this is how you solve ODEs with undetermined coefficients. Hey everyone, so we're on our second example for today's solving ODEs with undetermined coefficient method, and we're gonna start with writing down our superposition principle, which we're gonna apply later, which is yc plus yp, and solving for the homogeneous part is pretty straightforward again. R squared minus 4 equals to 0. We can see here r is equals to plus or minus 2, so we can just directly write down our yc is equals to c1 e to the negative 2x. Remember, our independent variable is x, so we shouldn't forget that. Always look at the right hand side, because usually they use t, plus c2 e to the 2x. And so let's denote this as our first equation. And then we're gonna solve for our yp, which is for our non-homogeneous part. And for this, remember always to look at the form on the right hand side. And since we have an exponential form and also we have a polynomial form, because 8 is some kind of a polynomial form, we can combine both polynomial and exponential, and we can increase the degree by 1, because if we don't increase the degree by 1, you're going to get stuck and you're not going to be able to solve for the coefficients later. So increasing the degree by 1, we can make it ax e to the 2x, taking the first derivative, we use the product rule, a e 2x plus 2ax e 2x. Taking the second derivative, we use the product rule again for the second one. The first one is without the product rule. This is the second one, and we get 4ax e to the 2x, and this is just 4a e to the 2x. And now plugging our equations here, like the previous problem, to our original ODE, so we can solve for the coefficients. We get here y double prime is 4a e to the 2x. We combine both of these terms, plus 4ax e to the 2x equals to 8e to the 2x. Actually, we forgot one variable here, which is the y. Minus 4 times y, which is yp, is 4 times a x e to the 2x, and everything here is equals to a 8e e to the 2x. And so we can cross out the terms here because we know they cancel each other, and we're left with 4ae to the 2x equals to 8e to the 2x. And solving for a here is pretty straightforward. We get a equals to 2, and plugging back our a to our yp, we'll get here 2x e to the 2x, and plugging our second equation for our yp and our first equation for our yc to our superposition principle, we'll get a general solution of y equals to yc, which is c1 e to the negative 2x plus c2 e to the 2x and plus 2x e to the 2x. So this is our general solution for solving this ODE problem. But normally we would stop here, but we need to look back at our problem because we have an initial value problem here, or initial conditions to begin with. And so we're gonna use these initial conditions to solve for our C1 and C2 both coefficients, like solving previous ODE problems. And so using our first condition, which is y0 equals to 1, y0 equals to 1, plug that in our equation third here, we're gonna have C1 e to the 0 for every e to the 0 is just 1. So we can write that as C1 plus C2, and 2 times x, which is 0, is just 0, so we can ignore that. And everything is equals to 1. And our second initial condition is y prime 0 equals to 1. Y prime 0 equals to 1. We're going to take the derivative of our third equation, our general solution, which is negative 2 c1 e to the negative 2x plus 2c2 e to the 2x. And this is a product rule, which is 2e to the 2x plus 4x e to the 2x. And then we're gonna plug in 0 for every x and equate everything to 1, which we will get here negative 2c1 e to the 0 is just negative 2c1, and also for the plus 2c2, and plus 2 e to the 0, which is plus 2, plus 4 times 0, which is 0, and everything here is equals to 1. And now we can move the 2 to the right hand side, which we will get negative 2c1 plus 2c2 equals to negative 1. And we have two equations here. We can use elimination or substitution to solve this. I prefer elimination because for me it's pretty fast to solve it. So we can see here that we can solve this by elimination. Forget this is C2, not C1. And yeah, we can multiply the second row by 2. We can add it up. So the C1 cross out because negative 2C1 plus 2C2 plus 2C1 is 0. And then 2C2 plus 2C2 is 4C2. Wait, we used the wrong color here. 4C2 equals to negative 1 plus 2 is 1. So we get here C2 is equals to 1 over 4. Double checking, -1 plus 2, yep, is 1. And so we have our C2, we just need to plug it back to our equation. We can choose between this equation or here to get our C1. We're gonna choose here C1 plus C2 equals 1 because it's easier. And then we'll get C1 plus 1 over 4, plugging our C2 equals to 1. And so we'll get here C1 is equals to 3 over 4, 1 minus 1 over 4. And we get both of our coefficients here, C1 and C2. We just need to plug them in, plug them back into our general solution, which is right here, our third equation. And so we'll have our final answer here as y equals to C1, 3 over 4, e to the negative 2x, plus C2, 1 over 4, e to the 2x, plus 2x, e to the 2x. And this is what we call our particular solution, as you all may know from the previous videos. Solution. And yeah, this is how you solve an ODE with undetermined coefficients, provided initial conditions at the start of the problem. Hey everyone, so this is our last example for today's solving ODE with undetermined coefficients. So we have here a higher order ODE, which is not the second order anymore. But solving this is pretty straightforward, and we use the exact same steps as we solved the previous problems. So first of all, let's begin by writing down our superposition principle as what we did in the previous problems. And we begin by solving our homogeneous part, which is our yc, which is r cubed minus 6r squared equals to 0. And we can factor out the r squared, which is r minus 6. And we get here r equals to 0 as one solution. And we get r plus 6 as another solution. So our homogeneous solution, or our yc, will be, since this is a repeated solution, we have here c1 e to the 0, because r equals to 0, which we don't need to write that, and plus c2 x e to the 0, which we don't need to write e to the 0 again, because e to the 0 is equals to 1, plus c3 e to the 6x. And let's denote this by our first equation, so we do not forget. And now let's solve for our non-homogeneous part, which is our yp. And pay attention here, we're not dealing anymore with exponential form, but we're still dealing with polynomial form because we got the 6 here, and we're dealing with a sinusoidal form because we got the cosine of x here. And usually we can combine both of this like what we did previously in our exponential part, which combining both polynomial and exponential part in one form of yp, and we take the derivative based on our original equation. But we can also split it up to make our equations looks easier and to solve for both equations. So our yp of 1 here, our first part, which is our polynomial form, we're gonna write ax squared plus bx plus c. And the reason I use the squared polynomial form, because our general solution is already in a degree 1 of polynomial. So if we put another degree 1 here, we will not be able to solve for our coefficients that we desire. So taking the first derivative, as usual, 2ax plus b, second derivative of yp1 is just 2a, and our third derivative of yp1 is just 0 because 2a is just a constant. And the reason why we take until the third derivative, because our original equation is up to third derivative. And so solving for our yp of 1 here by plugging our equations here to our original equation here, we will get the third derivative is 0, so we don't need to write that down. Negative 6y double prime, our y double prime is 2a, negative 6 times 2a is negative 12a, equals to 6. So we get here our a is just negative 1 over 2. And so our yp of 1, our yp of 1 here is just negative 1 over 2 x squared. We can forget about bx plus c because we don't need the b and c coefficients as it doesn't show up here. Or if you want, you can start the equations with just ax squared because this is redundant to begin with. And so let's solve for our second non-homogeneous part, which is our yp2, which is in the form of sinusoidal. We use a cosine of x plus b sine of x. Remember why we use a and b? Because negative cosine of x is the same as negative 1 times cosine of x, which has a polynomial in it as well. And so taking the first derivative, we'll get negative a sine of x plus b cosine of x. Taking the second derivative of yp2, we get here negative a cosine of x minus b sine of x. Taking the third derivative, we have here positive a sine of x and negative b cosine of x. After we have it here, we have the equations here, we're going to do as our usual, plug the equations in our original ODE and solve for the coefficients. And so we have here yp2, the third derivative of yp2 is a sine of x minus b cosine of x minus 6 times y double prime, and our yp2 double prime is negative. Let's write this down as this so we don't confuse it. Let's put it inside a bracket so we don't mix up the signs, we don't make silly mistakes, which people tend to make usually because they don't use the brackets here, and equals to negative cosine of x. And so we have here, and let's simplify for our equations here. We have it a sine of x minus b cosine of x plus 6a cosine of x plus 6b sine of x equals to negative cosine of x. And since we have here our sine of x and cosine of x, we will group them based on either their sine of x or cosine of x, like in the previous examples where we group them if they have the same polynomial degree or different polynomial degree. And so our sine of x, we have it here as a plus 6b, as you can see here, is equals to 0. Let's rewrite that down. 6b equals to 0. And our cosine of x, we have here negative b and 6a. So 6a minus b equals to negative 1, because we have the coefficients of cosine of x as negative 1. And so we use the same method that we used previously, elimination or substitution. You may use either. And we multiply the second equation by 6. So we can cross out this piece because 6b minus 6b is plus minus 6b is just 0. And so we have here as a plus 36a is just 37a. We use the wrong color. 37a equals to negative 0 plus minus 1 times 6 is just negative 6. So we have it here as negative 6. And then we have our a as negative 6 over 37. Or I guess we make a mistake here. We multiply the first equation by 6, and so we minus them, We subtract both equations. We can get rid of the a's, and for the b we'll get 36b minus b, which is 37b, equals to 0 times 6, 0 minus 1, which is 1. So we get here b is equals to 1 over 37. I think we did correctly previously, but we can also do this. Multiply 6 on top and minus both, subtract both equations instead of adding both equations. And so now we can solve for a because we have b. Then we can plug our b here to our first equation here, or our second equation because we don't have any coefficients in front of b, which makes the calculations easier. 6a minus 1 over 37 equals to negative 1. And so we have here 6a equals to negative 37 over 37 plus 1 over 37. We have here 6a equals to negative 36 over 37. We can multiply both sides by 1 over 6, which we will get here. A equals to negative 6 over 37. And so this is our A and this is our B. We have both A and B's. We can plug them both back in our YP2, which is here. Remember, A cosine x plus B sine x. So our A is negative 6 over 37 cosine of x. And our B is 1 over 37 sine of x. And so we can plug both of our second equation and third equation, and also our first equation, obviously our complementary solution, to our superposition principle that we stated at the start of the problem. And this is our final solution. Y equals to yc, which is c1 plus c2x plus c3 e to the 6x minus 1 over 2 x squared, our yp of 1, and our yp of 2, minus 6 over 37 cosine of x plus 1 over 37 sine of x. And this is how you solve ODEs using the undetermined coefficients for higher orders in sinusoidal form.